the first talk will be Surya Gunasekar talking about some of the newer implicit regularization we've been doing.
Thanks, Masood, for the introduction. Thank you all for coming. Today I'll be talking about kernel and deep regimes in over-parameterized learning and some very simple over-parameterized learning to be precise. And this is joint work with Blake, who is the only person who's not here. Then Jason, Daniel, and Nati, all of them are around, so you can bug them for questions. So as we have heard many talks over this workshop and the program itself, like the prominent mode we use deep learning in practice is to train very large neural networks on very large scale data sets. And the key component of this entire learning process is some form of loss minimization over examples using variance of gradient descent. This is typically some form of accelerated stochastic gradient descent. And another prominent aspect of deep learning used in practice is that they are often over-parameterized models. And over-parameterization is typically defined as the setting where the number of effective parameters is larger than number of examples. A somewhat more functional definition for our purposes today, you can think of over-parameterization as a setting where the model class has multiple functions which globally minimize the loss objective. And more importantly, we want to think of all these minimizers as distinct functions in the sense that they have different properties in terms of the learning goal we really care about, which is how well we do on new examples and so on. And in many, though it's not always the case, in many settings, and certainly in all the settings I'll be talking about today, in over-parameterized models, the minimum loss on the training data is typically 0. So there exists at least one model, and in this case, multiple models, which fit the data with 0 loss. So since the objective in this case is like ill-posed in a sense that there are multiple minimizers which have very different properties, it's kind of intuitive to think that the optimization algorithm used to minimize this objective kind of plays a crucial role, not just for optimization, but also in determining statistical properties like generalization and so on. So you can think of different optimization algorithms traveling this landscape and reaching different points. And in doing so, they implicitly introduce different forms of inductive biases into the learning process. And one of the key questions I'll be focusing on today is what does gradient descent for different over-parameterized model converge to in some of the some interesting settings we'll be looking at. So going back to this generic loss function, we can decouple, or to some extent decouple, the question into 3 sub-questions. The first is understanding when does gradient descent converge to a global minimizer at all. And this is purely an optimization question. And typically these losses are non-convex losses. And there is an interesting line of work which is exclusively studies the optimization question of when we converge to a global minimizer. And the second question is, because it's an ill-posed problem, which of the many minimizers does gradient descent converge to? And this will, in some sense, be a focus of today's talk. And presumably, we are learning over-parameterized models and having good performance on new examples. It is reasonable to guess that the gradient descent on these models are learning some predictors with small complexity for some notion of complexity. And finally, the question is, how well these models, or how to connect these notions of complexity to actual generalization bounds or other properties we care about the learned model itself. So as I said, I'll primarily be focusing on the second question. So the third question, at least for the models I talk about, Peter, if he's around, he's already given an answer a long time back. And for more neural network papers, probably Carolina and Misha talked about it later. And as for the first question, again, in all the results I state, even if I don't explicitly mention, we kind of start with the assumption that the gradient descent minimizes the loss function. That is, it reaches a global minimizer, and we focus on the second question. Again, for the settings we will be talking about today, which are mostly linear models, this question has been answered positively, say in a sense that for almost all data sets, the first question holds. It does hold that gradient descent reaches a global minimizer. So to introduce some notations for today's talk, so we have this generic loss function, over the parameter space. But what we really want to understand is what happens in the function space, what happens in the prediction space. And for that, I introduced this mapping capital F, which maps parameters to some prediction function. So you can imagine this, this function space being like set of all linear predictors, or set of all the functions implemented by a neural network, and the parameters being specific weights of the neural networks, or specific weights of a linear network, and so on. And what we want to understand is what happens when we do gradient descent on the parameter space. This, of course, introduces a series of iterates in the function space, and we want to reason about what the complexity of the functions learned by gradient descent in the function space. And so one way to do this would be to bound what the iterates, say that the iterates in the parameter space are confined to some small region of the entire space, and that would lead to some complicated complexity measure on the function space. And understanding this connection is an interesting area of research in itself. So to make this formalism very concrete for a simple problem, we look at matrix completion. So matrix completion is a simple problem where we have a ground truth matrix, we observe some entries, and the goal is to fill in the missing entries. A natural objective to write for this matrix this problem is to write a least squares objective where we are just fitting the observed entries. But this optimization problem as written here is a very trivial optimization problem. I mean, all I'm asking here is like fitting the observed entries with the observed entries. And in other words, any imputation of the missing entries is a global minimizer of this problem. So this is a setting where the objective is a convex optimization problem, but there are multiple global minimizers which give you zero loss. But we are going to insist on solving this optimization problem, not in this direct form. We'll solve it in the direct form too, but in a slightly different variation, where we write the matrix we want to estimate W as a product of two matrices U and V. And this is indeed a formulation used to introduce like some notion of low rankness. So if I restrict the size of U and V, I'm explicitly constraining the rank of the matrix I'm allowed to learn. And in which case, like these two objectives are very different. But in this case, I'm not restricting the rank in any way. U and V are full dimensional matrices. So these two optimization problems are exactly equivalent. All I have done is take a simple least squares problem and turn it non-convex. Okay. All the imputations of the matrix are global minimizers of both these objectives. And now we're going to see in a toy example of this problem, what happens if I do gradient descent on the original objective over the matrix directly versus gradient descent on the factorized objective over U and V. And when we ran this experiment, we found something very interesting. First is that both gradient descent on the original objective as well as gradient descent on the factors converge to a global minimizer, so which can be seen by non-existent training error bars. But what is surprising is that doing gradient descent on the factorized objective also gets us solutions which have good performance on new examples, which are unobserved examples. And even more surprisingly, we found that like instead of using exact line search in the gradient descent for factorized objective, if you use a small step size, we get to solutions which have even better performance on the new examples. So what's happening here is that we have three different algorithms effectively optimizing the same objective. The underlying space of solutions is the same, but they clearly lead to different global minimizers because this is a problem where there are multiple global minimizers. And in particular, doing gradient descent on the factorized objective with small step size leads us to something interesting which has very low performance on new examples. And in this experiment and many other experiments we conducted, we could empirically see that this special solution we converge to is indeed a minimum nuclear norm solution. So we can think of a solution where I explicitly minimize the nuclear norm subject to fitting the data, and the solution we converge to is equivalent to this explicitly nuclear norm minimized solution. So this was one of our early observation, and this also extended to other cases of matrix estimation from linear measurements. So matrix completion is a special case where the linear measurements are individual entries of the observation, But for more general linear measurements, we can write the corresponding factorized form. As long as the number of linear measurements is smaller than the number of size of the matrix, this is a nil-post problem with multiple minimizers. And the factorization itself you can think of as like a two-layer network with linear connections, linear activations. And in these settings, we wanted to understand more theoretically when does gradient descent on the factorized objective converge to a minimum nuclear norm solution. And in the experiments, we found this to be the case when the initialization is close to 0 and the step size is small. And in our original paper, we had a theoretical result where we showed that this holds for very, very special class of measurements called commutative measurements. And this in fact doesn't cover the matrix completion or random matrix sensing setting, but it has interesting corollaries for some vector problems which I'll come back to later. And aside from commutativity, the theorem holds for infinitesimal step size. So we formulated infinitesimal step size by looking at the gradient flow, which is taking the gradient descent, taking the step size to 0, which leads to a differential equation over the parameters, and we look at the limit of this differential equation. And the other infinitesimal we consider is like infinitesimal initialization. So we not only look at the limit of the ODE, but also look at what happens when the initialization is gradually set to 0. And follow-up work, one by Li, Tengyu, and Zhang, extended this result to general forms of Gaussian random measurements, which have, or in other words, measurements which satisfy the restricted isometry property, and also to two-layer networks with squared activations with Gaussian inputs. And an even more recent result by Sanjeev, Nadav, and Luo show experimental and theoretical results for higher depth network, where instead of having 2 factors, imagine having multiple factors. And they show experimentally and theoretically, they study this setting in more detail, and Nadav talked about it in yesterday's talk. So we see that in this simple setting, we demonstrated that like gradient descent can implicitly introduce very rich form of inductive biases. In this case, it's nuclear norm, or for good measurements, it's also equivalent to minimizing the rank of the matrix. And we have since like shown similar kind of results for some other cases. In particular, a simple corollary of the existing theorem itself shows that if I have a underdetermined least squares problem, so I have a vector problem where beta is the vector I want to estimate, but instead of writing the least squares problem directly in terms of beta, I write it as in terms of the parameter squares. So I write beta as like w squared and do gradient descent over the least squares objective. In this case, it can be shown that gradient descent with infinitesimal initialization and step size goes to a minimum L1 norm solution. Here again, we get a sparsity inducing norm implicitly from gradient descent. We also looked at more results in like a classification setting, where we look at exponential tail or logistic kind of losses. And in these cases, one interesting solution we had is like if I had linear convolution network. It's a linear network, but each of the layers has a convolution operation. It's a full dimensional convolution operation. And in this case, we were able to show with some assumptions that the gradient descent iterates eventually lead to a predictor which is equivalent to minimizing some sparsity inducing norm of the Fourier coefficients of the effective linear predictor. So, I mean, you can think of roughly as like doing some sort of frequency filtering in the linear function space. The 2 by L norm is not always a norm, so it's sometimes non-convex. That's why we converge to stationary points of this objective. And more generally, like more recent work, especially by Kaifang, Liu, and Li, which give the strongest result in this setting, and they also build on some of our earlier work, show that like if I have a homogeneous model, any mapping which is homogeneous in the parameters, I'll come back to what is homogeneous mapping soon, then the doing gradient descent on the parameters or gradient flow on the parameters converges to stationary points of minimizing the Euclidean norm of the parameter subject to margin constraints. And here you can see that like even if the function class is same, by changing the parameterization, we actually get different biases. And same has been the case even in these settings. All I have changed from like between these two models is just change the parameterizations, and we get very different biases. So this was the state of like some of the results. This was a summary of some of our earlier work, and so as I was like, as we were working through this, there was another parallel line of work, which was, sorry, I forgot to mention that these two results again hold under further assumptions. Yeah.
So in all of these results, what is the initialization?
So for these two, they are infinitesimal initializations.
Oh.
And here, the initialization is just anything non-degenerate, like for almost all initializations. But like there are other assumptions which are involved, and you can look at the papers for detail. So as we were working, there was another parallel line of work which also explained what gradient descents can converge to an over-parameterized regime. That is neural tangent kernels. And I wanted to do a very extensive survey of this line of work, but this is my current understanding of this line of work. And okay, so I'll just try to convey my intuition. So think of any nonlinear function. You can roughly approximate a nonlinear function by doing a Taylor expansion locally. So you have some initialization W0. You do a Taylor expansion. This is just a first order, zeroth order term, the first order term, and a second order term. And if suppose your optimization algorithm ensures that you never move too far from the initialization, right? Or rather, your optimization algorithm converges before you move much further, in those settings, only like the first order terms will matter. Like the second order term and higher order terms will not be significant. And so we can define this alternate linear models, and the first order term is simply a linear model in the parameter. So we can define this alternate linear model, which essentially just keeps the zeroth order at the first order term and ignores everything else. Okay? And I'm introducing capital F bar just to denote the mapping for notational convenience. And a kernel regime or neural tangent kernel regime, in my understanding, is essentially like the settings under which, like for up to certain time t, it is ensured that like the functions in these two, doing gradient descent on the original function versus doing gradient descent on this linearized function have roughly like the same, are roughly like the same in the function space. They might differ in the parameter space, but they roughly have the same function value. So they roughly have the same functional representation. Okay? And in this setting, especially like for the neural tangent kernel setting, the models learned by gradient descent are effectively linear models over some feature map. And here the feature map is given by like the gradient of your original nonlinear function around a fixed point, which is like your random initialization. Okay? And so this so if I have a result which says that for time t less than capital T, these two function paths remain the same, and also that within time t I converge to a good solution, that means roughly we have shown that, at least in the hand-wavy way, we have shown that doing gradient descent on this nonlinear function will converge to a good solution, which is simply which is very close approximation to a linear function. And so this feature map introduces a kernel which we call as neural tangent kernel, and we can now ask what is optimization bias in the kernel regime. Let's say this is what is happening, that when we do gradient descent on the nonlinear function, we are effectively learning this linear mapping. Then we want to understand what is the optimization bias in the kernel regime. This is still a very high dimensional linear setting, so you still have over parameterization. But just adapting the existing results for this special case, you can show that you can precisely characterize what is the optimization bias. In particular, if you are minimizing something like a squared loss with a unique minimizer, then you will converge to a very specific function which minimizes the RKHS norm in this neural tangent kernel space, the RKHS norm distance between from the initialization. So in particular, if I initialize in a way that the function at initialization is 0, the function returned by doing gradient descent on the neural tangent kernel is simply something which minimizes an RKHS norm. subject to fitting the data. And similarly for logistic loss, you can show that in this regime, the function or the prediction function you get is essentially a max margin solution, which with respect to this RKHS norm, right? Where the RKHS is given by this kernel. So we want to, so this is the optimization bias of neural tangent, the kernel regime itself, this neural tangent kernel based linearized function. But mainly what we really wanted to understand is like what does gradient descent on this function show, the original nonlinear function converge to. And in this case, the other part of the question is like when are these two functions equivalent? When are we actually in the kernel regime? So there is a lot of literature on this, but we'll focus on special case when the functions we care about, or the nonlinear functions we originally started with, are homogeneous functions or positive homogeneous models, where if I scale the parameters by some scalar quantity, positive scalar quantity, the function itself doesn't change the direction, it only gets scaled by some power of the positive scalar quantity. And for these homogeneous models, we write down the corresponding linearization around the first order approximation. And we want to focus on squared laws for now. So we can write two equivalent squared losses, one over the original function class and the other over this restricted linear function class in the RKHS space. And we run two gradient flows. Both of them are initialized at some scaling of some non-degenerate point. W0 is some non-degenerate point, and alpha is a scaling. And we run two gradient flows. One is doing gradient flow on the squared laws over the original class of functions. The other is doing gradient flow over the squared laws of this tangent kernel space of functions. And the question is like, when are these two gradient flows somewhat similar? So this is the rough idea discussed in this whole lot of papers, and I'm pretty sure I missed a lot of them. These are essentially like the list for which at least I read the introduction of. Anyway, so for our purposes today, we are going to focus on squared laws to begin with, like for the next 5 to 10 minutes or so, and look at these two gradient flows. I'll present a very simplified setting where the kernel regime definitely holds, and that is essentially adapted from Chizat and Bug's notes on like lazy training something, and which essentially says that if my initialization, the scale of my initialization is going to infinity, then the two function classes are roughly converging to each other. So the function paths are in these two regimes converge to each other. The actual theorem in Chizat and Bug itself is not working in this asymptotic regime. They actually give like the rates of convergence and so on. It is much more detailed, but just to keep things simple, we'll only work with these asymptotic regimes. And from an earlier discussion, we also know that if we initialize in a way that our function at initialization is 0, then we are effectively in the kernel regime, and we know that in a kernel regime we converge to a specific solution, which is the minimum RKHS norm solution for squared laws, right? So this is indeed a theorem. So we see that for any homogeneous models, if I take the initialization scale to infinity, we converge to a minimum RKHS norm solution. But this also stands in contrast to what we have earlier seen, where we showed that for squared laws again, for homogeneous models, we can get biases, interesting inductive biases, which are not minimum RKHS norm solution. And the catch here is like these answers were proven in like the initialization going to 0 regime, whereas the kernel regime seems to hold when the initialization goes to infinity. So, and we wanted to further investigate this connection. Is there a transition, or is it just these two asymptotic regimes we can understand? And in reality, we really want to understand what happens for finite alpha. And for matrix factorization, we just use, for matrix completion problem, we use the same factorized model. We just adapted it so that like our initialization is 0. And in this case, like we computed what the RKHS kernel is. So if we want to look at what minimum RKHS norm solution for this problem is, it is a very trivial solution where you just impute the missing entries with 0. Okay? So you don't move the missing entries at all. But what we seen previously is that we don't get those trivial solution, we get something rich. And now in this experiment, what we do is like vary alpha between very small quantities and very large quantities and see the transition. So on the top, we essentially show recovery of ground truth matrix. So wherever it's white, it's essentially where you're getting a minimum nuclear norm solution. And hence you are not in the kernel regime because minimum nuclear norm is not the RKHS norm. And on the bottom, what you see is like how much the unobserved entries have moved. So the white regions are essentially like where you see kernel regime happening. And we see that like for different number of ranks, which are in the over-parameterized regime, there is a phase transition between the two cases. So this was an empirical observation, and we wanted to actually understand in some simple setting an analytical version of this transition. So far what you have seen is an example where the optimization bias from gradient flow seems to transition somewhat smoothly between the kernel and deep regime based on just the scaling of the initialization. And in the rest of the talk, we see a more analytical example of where this transition can be made more precise. And more generally, like things I won't talk about much today is this transition could also depend on the loss function, which we are using, squared loss versus logistic loss, and the step size and number of iterations. But yeah.
On the previous slide, when
Yeah.
you take or maybe 2 slides back, sorry. That when you take that double limit, is it generally alpha and t scaling together at some particular rate, or is it really just simultaneous?
No, I was taking t to infinity first. It's really supremum over t, but that requires some additional technical assumptions. So you only need to take alpha to infinity to make it 0. And in reality, you don't need these 2 limits. You can take supremum over t, and you have here 1 by alpha or something. Like the gap is 1 by alpha. Okay. So the things I specifically won't talk about is like the step size and number of iteration, because we'll still be working with gradient flows setting and we'll be looking at the asymptotic solution when the optimization algorithm has fully converged. Okay. So,
Question, that's just an upper bound, right? We don't know
Which one?
The limit.
which limit?
The limit is an upper bound. So if under this condition those trajectories are closed, but they may be closed under other conditions as well. Which are not covered.
Oh yeah, they may be closed in other conditions as well, but if they are closed, we won't see the minimum nuclear norm or minimum L1 norm behavior because they are definitely not. So at least in this figure, it's clear that there is a region where they are not close because you're recovering minimum nuclear norm solutions, which is very different, at least for this problem. So in order to analytically understand this transition, we'll look at even simplified problem than matrix completion, which is linear regression with squared parameterization. So here our function is simply a linear model of the inputs, but not necessarily of the parameters. And in particular, the linear functional is parameterized as using two times the dimension of the input itself, where the functional parameterization is W1 square minus W2 square. So I have 2D vectors. So W1 squares are element-wise squares of the first D vectors, and I'm subtracting W2 square. And the reason we go with this kind of weird initialization is so that it allows us to start with 0 initialization. As long as I set W1 equal to W2 at initialization, my initial prediction will be 0. And that makes the analysis somewhat simpler. But you can also, like, this is a very simple setting, you can also solve it for more general cases. And we'll be studying gradient descent with infinitesimal initialization, where the initialization is essentially scaled identity. So W1, not scaled identity, scaled all ones vector. Okay? And we'll be looking at a gradient flow dynamics, which is just doing gradient descent on this squared loss objective. And what we really care about is like what the dynamics mean in the function space, which is what happens in the beta space, the effective function learn space. So for this setting, from existing work, we already know what happens when alpha goes to 0 and alpha goes to infinity. So for alpha goes to 0, our work from 2018, actually it's 2017, showed that like as long as the limit when alpha goes to 0 exists, you will recover a minimum L1 norm solution. And for alpha going to infinity, it's again adapting from Chizard and Buck's paper and many of the other neural tangent kernel papers. You can show that if the limit alpha goes to infinity exists, it has to be the minimum L2 norm solution. So these are the two extremes we can get. Now we can ask what happens when alpha is not in between these two extremes. And here, for this particular case, we can actually explicitly calculate what happens. And so what we end up showing in a new work with Blake, Jason, Daniel, and Nati is that for any finite alpha, the solution returned by gradient descent is something which minimizes some complexity measure subject to fitting the data. And this complexity measure is, I have no intuition for where this comes from, it just comes from calculations. Maybe Nati has a better intuition. Okay?
It has a name also.
Yeah, it has a name, it's called hyperentropy. I don't know where the name comes from. Well, I know where the name comes from, but I don't know the intuition behind the name either. So this is just like, okay, I don't want you to parse this equation, but you can show visually what this equation does.
Sorry, can you give the conditions on the theorem?
So the condition on the theorem is that the loss converges to 0.
And do you have these gradient converges assumptions?
No, so this is for squared loss, there's no gradient
You're
convergence.
assuming the loss goes to 0.
Loss goes to 0, and for this case there are no bad local minima because this is a linear problem with squared loss. And we know that there are no bad local minima, there are only saddle points. And I mean, essentially mapping from existing work, we can argue that for almost all data sets, you will converge to 0.
So just so I understand, so you're taking, you're specifically considering these settings where the alpha is too large to apply.
Sorry?
That's what I'm confused about here because it really is alpha greater than 0.
Alpha is anything which is not 0 and not infinity, because the limits of alpha going to 0 and alpha going to infinity we saw in the previous slide.
Right.
So, I mean, I wanted to, so in one alpha going to 0, we saw this minimum L1 norm solution. And alpha going to infinity is this kernel regime where we saw minimum L2 norm solution. Wanted to understand what happens for finite alpha.
I'm just trying to figure out why, if we could remove this assumption of losses going to 0.
Yeah, so you can remove the assumption because there is existing work which show that there are no bad second order stationary points for this problem. It's just, didn't want to include it in the paper, yeah.
When the loss should always go to 0 once you have enough parameters, right?
So, I mean, there are definitely, if you start at saddle points, it won't go to 0.
Sure.
If you start at W1 equal to 0 and W2 equal to 0, the gradients will be 0. There are saddle points for this problem, but existing results already show that there are no second order stationary points. So as long as if I start from a non-degenerate point, it should go to, at least gradient flow should go to 0. Right? So essentially patching like no bad local minima and Jason's work that gradient flow doesn't get stuck at saddle points, loss going to 0 is not really a big assumption here. Okay, so instead of parsing this equation, I can visually show what this equation looks like. So it's essentially like summing over some quantities along each coordinate. And this quantity we are summing over has a structure like this. And we know, and just even by looking at this functional form, we can show that as alpha goes to infinity, this function q alpha of beta essentially is proportional to L2 norm of beta. And as alpha goes to 0, so one thing is z is inversely proportional to alpha, so I should have plotted in terms of alpha. So z is essentially beta by alpha square, so alpha going to infinity, z goes to 0, in which case it looks like L2 norm. And alpha going to infinity is z going to 0, where it looks almost like L1 norm. And you can explicitly quantify what rates they approximate the minimum L1 norm and minimum L2 norm solution. In particular, to get into the kernel regime, at least for this problem, it seems like you only need a polynomial sized alpha. But in order to get into this rich regime, we see like, the constants are there in the paper. I'm just using order notation for the talk. So we see that for the rich regime, like we need like really, really tiny alpha to get minimum L1 norm solution. Close to the real minimum L1 norm solution. Sorry, the L1 norm from gradient flow close to the minimum L1 norm solution. And of course, like in L1 norms are useful for sparse learning problems. And sparse learning problems. So we use a simulated sparse learning data set, and the first we just essentially showed that like you can plot the excess L1 norm and excess L2 norm. This shows how essentially like the shift bit from kernel to deep regime is. Here deep regime is essentially the L1 norm regime. I'm calling it deep because it cannot be represented by our KHS norm. So as we see alpha going to 0, you get like the excess L1 norm goes to 0, so you get L1 norm recovery, and the other way around for very large alpha. And a more interesting plot for this setting is to see what is the number of samples I need to recover with a particular alpha. So because we know that alpha going to 0, I'll get minimum L1 norm. And we know the minimum L1 norm solution requires something like k log d samples, where k is the sparsity. Right? And this is the dashed line. We can also plot what is the minimum number of sample needed so that the recovery is like has some error less than some threshold.
Do I understand correctly that every other norm for alpha not equal to 0 is actually an L2 norm?
No, it is something in between. It is exactly the Q alpha thing.
But isn't it just a reweighted norm? You're reweighting.
This is not necessarily a norm, right? This is just some complexity measure.
I see.
Yeah, it is not necessarily a norm. It's some interpolation between L1 and L2 norm, like interpolation not in the interpolation regime sense, the real interpolation sense. Okay. So I'm actually like, I thought I'll finish quickly, but I'm actually running out of time. So I just wanted to mention one other connection, which is relationship to explicit regularization. As I said, like the complexity measure we come across is very non-intuitive. A more intuitive guess, if I had thought about this problem a while back, would be saying that gradient descent is biased towards solutions which minimize the distance to the initialization, where the distance is measured in Euclidean norm, right? And so I would expect, my guess would have been, or many people's guess would have been, that I'll converge to a function where the parameters are something which minimize the L2 norm to the initialization. And the reason we would have guessed this is because there are many previous characterizations where the optimization bias was explicitly related to optimization geometry. And in particular, if you think about how we do gradient descent iterates, it is effectively by doing this local regularization where going from one step to the next step, we penalize in Euclidean norm the step length. So you want to move along the negative gradient direction, but you penalize the step length in Euclidean norm. And that's how we get the gradient descent iterate. So it's kind of intuitive that if I'm penalizing the step length in Euclidean norm in each step, I'll get to something which is minimizing the Euclidean distance to initialization. And that is indeed the case in many of like previous results we have explored. But for linear regression with squared parameterization, we have this bizarro function looking thing. So we can also compute what this function would look like, what an explicit regularization with from initialization will look like. That I'm denoting as R alpha of beta, and we can show that this again interpolates between L1 and L infinity. So for alpha going to 0, this will be close to an L1 norm, and for alpha going to infinity, this is another L2 norm. But again, R alpha of beta is not a good looking function either. It's what Mathematica solved it for us. It's some roots of some polynomial. But to look at it visually, like this is again looks like another interpolation thing, but it's not exactly Q alpha. So the connection is somewhat tenuous. This intuition does not hold, at least for this squared parameterization case. And another example I know of where this intuition fails is like what Nadav talked about like day before yesterday, I think, where even for deeper linear networks, he showed that doing squared laws returns minimum L1 norm solution, whereas minimizing this distance to initialization would return something very different. Okay. So so this was the main part I wanted to cover about like looking at squared loss settings and analytically look at this transition in a very concrete way. I just wanted to share some thoughts about like logistic loss. Can I take a couple of minutes?
Free.
Yeah, okay. Yeah. So been working with like both implicit bias of both squared loss and logistic loss, we have found that logistic loss works in a completely different regime. So in particular, if I have separable data sets, think of any loss which has a strictly decaying tail, like logistic loss, exponential loss, and so on. And if the data set, for example, here it's linearly separable, but for any function class, you can think about data sets which are separable by that function class. And in all these cases, if the function class is homogeneous, there are no finite minimizers of this loss function. As a consequence, if the gradient descent is actually minimizing the loss, the norm of the iterates will converge to infinity, go to infinity, it will not converge. So we cannot ask what does gradient descent converge to in this case. What does the parameters of gradient descent converge to? But for these problems, what makes things simpler is that we don't really need to care about exact parameters. What we really care about is like what does the direction of the gradient descent iterates converge to, and what is the function induced by those directions. Because if f is homogeneous, I can just take the norm out. That is effectively like a scaling of the decision boundary. So the only object we need to worry about is this, functional representation of this normalized direction. And so this A makes things simpler because when we are normalizing by these infinite quantities, a lot of things become simpler. But on the other hand, it also makes the process much more harder because now not only we have to argue that the loss converges, we also have to argue that the iterates converge in direction, not just in direction, and that this function is something interesting asymptotically. But there has been quite a few work on it. The main thing I would state is like the most recent result, which shows that by Kaifang, Liu and Li, which shows that for homogeneous models with exponential loss, if the gradient flow separates the data in finite time, then any limit point of the update direction, it doesn't have to converge. Any limit point converges to a stationary points of some max margin problem. So I don't want to go into details of it. But the main thing I want to point out is like, so this is independent of initialization and step size. So this, not step size, this is definitely independent of initialization. So even for finite initialization, this holds. And you don't need this alpha going to 0 business in this setting. And the reason is that for these exponential tail losses, the optimization path actually travels an infinite arc length. So if you think about where you finally end up, any finite initialization starts looking like 0 initialization. So that makes things a lot more simpler. There has been some work, I think Jason mentioned it, I couldn't actually locate the exact theorem, which shows that for finite time, gradient descent path is close to an NTK path. But as you take, because this gradient descent will not stop in finite time, as you take t to infinity, it eventually converges to this non-NTK regime or deep regime. And so this opens up some interesting problems, which is like how does the rate of convergence, yes, the asymptotic solution may not depend on the initialization, but how does the rate of the asymptotic bias, rate of convergence to the bias depends on initialization. And another problem which Jason pointed out in his talk too is like what happens if you start at an NTK solution? Can you more specifically characterize which of these stationary points you converge to and so on? Just some concluding remarks. I mean, the main thing I wanted to convey are the first two, which is optimization algorithms, even for some simple linear problems, can introduce non-trivial and often useful inductive biases, which are not in the NTK regime or any kernel regime for that matter. And what we focused on is like how the scale of initialization can facilitate the transition between the kernel and deep regimes. So the other factors which, as I said, could potentially influence this, the transition is like first step size and the number of iterations. As you can see intuitively, like NTK regime will hold if I quickly optimize the loss with very small step sizes, then I'm not moving much farther. And so understanding what happens if we use large step size and like, and understanding the transition based on step sizes would be interesting. But one of my main things I wanted to convey, even though I didn't have time to focus on it too much, is like the loss function plays a very important role. Like logistic loss is fundamentally different behavior compared to squared loss, and both the nature of the optimization bias and as well as like their dependence on hyperparameters like initialization and step size depends heavily on, changes very different, is very different when you use like logistic kind of loss as opposed to squared loss. So I would, this is one of the areas I would like some of you to think about in doing the work. Thank you for your attention. Sorry for going on.
We have time for one question. You have a couple
Yeah,
of
Mark was
No.
the question.
Oh, sorry. Okay, hi. Yeah, you can go.
Thank you. I was wondering, what is known about similar implicit biases for adaptive recommendation algorithms, like Adam or AdaGrad, if anything?
So there is a small result in one of our papers where we show that even for exponential laws, the answer depends on initialization and step size, which is more of a negative result, but I don't know of explicit analytical positive results.
Okay.
Yeah?
Yeah, I wanted to ask that model W1 squared minus W2 squared. So I understand that's what you work with because you wanted the overall initialization to stays 0, but that's not necessarily the only thing that one can look at. Did you try seeing just W1?
Yeah, so I mean we can characterize, especially for this least squares problem, you can actually track the path. So you can write down explicit characterizations for non-zero initialization and like even just W1 dot W2 and so on.
And W1 squared, for example?
W1 square, yeah, you don't get, so the issue is like you don't get L2 norm and alpha goes to infinity. You get some other kernel norm, but it's not an L.
It's possible to derive expressions.
It's possible to derive expression, in fact.
Okay, let's take speaker again.